Hello students, in this video I would like to discuss about analysis of heap sort. In the previous video we discussed about heap sort, and there we saw we have three main procedures. One is max heapify, next one is build max heap, and in the end we studied heap sort. So here in this video we will analyze these three algorithms. So here I want to analyze max heapify. You just go through the algorithm. If you notice it carefully, line number 1 to 9 always takes constant time because there is no for loop, there is no recursive calls. So line number 10 we have a recursive call. I will try to analyze this algorithm with the help of an example. This example we have already discussed in the previous video. So here I have a subtree. So what is the height of the subtree? The height of the subtree is 2. So here I am applying max heapify on a subtree with height h. The next step what happens? I applied max heapify in this subtree. What is the height of the subtree? It is 1. So earlier it is 2, now it is reduced to 1. In next step what happened? I applied max heapify to this node. Now what is the height of this subtree? The height of this subtree is 0. So just look at this recurrence relation. If I am applying max heapify on a tree with height h, that can be considered as time taken to apply max heapify on a tree with height h minus 1 plus 1. This plus 1 we already discussed because line number 1 to 9 will take constant time. We already studied on property. In a heap, if it contains n elements, then the height is log n. So h can be written as O of log n. So the complexity of max heapify is log n. So the running time of max heapify on a subtree of height h rooted at given node I is theta of 1 plus time to run max heapify on a subtree rooted at one of the children of node I, that is subtree of height h minus 1. So next we are going to analyze build max heap. So here is the pseudocode. Line number 1 will take constant time. This for loop will execute for n by 2 down to 1. That means this for loop will actually execute for n by 2 times. Every time it is going to call max heapify a comma I. So each call to max heapify goes O of log n, and there are n by 2 such calls because we already discussed line number 3 takes log n time, but how many times it is called? It is called n by 2 times. So the running time is O of n log n. This upper bound, though correct, is not asymptotically tight. The complexity of n log n is correct, but it is not asymptotically tight. So another analysis also there in the same method that we will see in the next slide. So the second analysis, this relies on the property that n element heap has height floor of log n and almost ceil of n by 2 raised to h plus 1 nodes at any height h. So we already discussed if a heap contains n elements, then the height of that heap will be floor of log n. And one more property we are going to discuss here. Here at most ceil of n by 2 raised to h plus 1 nodes at any height h. So for a given height h, if the heap contains n elements, there are n by 2 raised to h plus 1 nodes in that particular height. I'll try to explain that point with the help of this example. Here in this tree, how many nodes are there? 15 nodes. So the value of n is 15. So how many nodes are there with height h? We have only one node. The root node only have height h. So just compare with this expression. N is 15. What the height here? Height is 3. What is 2 raised to 3 plus 1? That is 2 raised to 4, 16. What is 15 by 16? It's some value near to 1. That ceil of that value is 1. So here in this example, the number of nodes with height 3 is 1. Similarly, how many nodes are there in this tree with height 2? Total number of nodes is n divided by 2 raised to 3. 15 by 8 is some value near to 2. Seal of that value is 2. Similarly, with height 1 we have 4 nodes. With height 0 we have 8 nodes. Next point, the time required by max heapify when called on a node of height h is O of h. This is discussed already in the previous slides. Before discussing the third point, you just look at this pseudocode. Here this max heapify is calling for values I equal to n by 2 down to 1. We already discussed this max heapify in the previous video. So actually this binary tree or this heap is represented in an array. So we already know the root is in index position 1. So for values in the index position I equal to n by 2, we are applying max heapify of a of I. Here it is 15. Floor of 15 by 2 is 7. So from the node at index position 7, we are applying max heapify. So actually this node is at index position 7. So we apply max heapify to these 4 nodes, then these 2 nodes, and then to root. Otherwise I can say first I will apply max heapify to all the nodes at height 1, then all the nodes at height 2, then all the nodes at height 3. That is the meaning of the summation, h equal to 1 to log n, 1 to 3. This expression gives how many nodes are there at each height. When h equal to 1, we have 4 nodes. So initially the summation will work for h equal to 1. Then it will execute for h equal to 2. Then it will execute for h equal to 3. So max heapify will be called totally these times. Each time what is the complexity? O of h. So we can express total cost of build max heap as, this is the number of calls of max heap, and each call it have a complexity of O of h. Here the summation depends on variable h. So n can be considered as a constant. So I am taking n out of the summation. So h is a dependent variable in the summation. So I am taking h inside. So this can be written as order of n sigma h equal to 1 to log n h by 2 raised to h. So one more thing, actually this 2 raised to h plus 1 can be written as 2 raised to h into 2. That 2 can be considered as a constant and it is discarded. That's why I got 2 raised to h here. Next I have a standard summation, sigma h equal to 0 to infinite h by 2 raised to h is approximately equal to 2. So for h value 0 to infinite, this sum of series is approximately to 2. So you just compare the summation and the summation. So the summation is also a constant whose value is much less than 2. Since the summation already gives a constant something approximate to 2, this also gives a constant 2. So that constant is discarded. So I can write this entire expression as O of n. In the earlier analysis I got the complexity as O of n log n. Here I have got a much more tighter complexity, that is O of n. Okay, next is analysis of heap sort. Line number 1 is build the max heap. We already discussed build the max heap. The complexity is O of n. So line number 1 takes O of n. Here this for loop executes n minus 1 times because length of a initially it will be n. So n to 2 means it is executing n minus 1 times. So during each execution this max heapify a comma 1 will be executed. We already studied the complexity of max heapify is O of n. So each call to max heapify takes O of log n. So the total complexity is O of n plus n minus 1 into O of log n. That can be written as O of n plus O of n log n minus log n. This O of n and this O of n and this O of log n will be lower order terms. So we will just discard it. So in the end we will get complexity of heap sort as O of n log n. One thing, the best case, the average case and worst case of heap sort is O of n log n. Thank you.